Now it is. Yeah. All right, we're trying to do 2 simultaneous recordings because I have learned that 30% of the recordings done automatically by the university usually don't work. So maybe today it's our lucky day because it's a Labor Day and we are working, right? So, okay. So the lecture today actually is a little bit ahead of the schedule, and which means we're going to come back to this topic to cover it in fine detail later this week and next week as well. Okay? But I want to give you things a little bit ahead of time because I assign you homework problems that require some of these things, but I have no idea how well I will be able to cover them before the due day of the homework. Okay? So none of them is so sophisticated that I will be concerned of asking you to do things without having covered these lectures here. So there are things you can deal with it. There will be, the notes would be on the web, et cetera, et cetera. Okay, all right. This concept of the rank is something, again, it's rather premature to discuss it right now, so we're going to come back to this topic after we introduce the concept of elimination matrices. And but let me just give you a very basic definition that we can use. We always have technical problems somehow. Okay, let me see. All right, there it is. Okay, so we are going to define for now, okay, with no much questions about it, the rank of a matrix to be the maximum number of linearly independent row vectors of A. We take this as our definition. So you look at the matrix, it doesn't matter if it's a square or 3 by 5, and you say, let's look how many independent row vectors we have. That's what we will call the rank of the matrix, okay, for now. Now, I am not telling you yet how to find out how many independent vectors a matrix has. This is something we're going to start covering in the lecture on Wednesday and Friday, okay? But if somehow you can do this and figure out the number of independent row vectors, we call this the rank of the matrix. All right, so we are going to introduce what I call these elementary row operations, which are basically operations that combine rows. So you can think, if you have a matrix, let's say 3 by 3, you can take the first row and the second row and you can add them and substitute row 1 with a new result. Or you can take row 3 and multiply with a number and change the order, put that as row 1 and put row 1 as row 3. This is what we call elementary row operations. So we call a matrix A1 to be row equivalent to a matrix A2 if A1 can be obtained from A2 by a finite number of these row operations. Okay? Now, again, this is a subject a little bit ahead of our schedule. So I have to tell you that on Wednesday, we're going to learn how to do these row operations using matrices. Okay? But today, I just want to introduce only the concept. So if you take a matrix A1, and you do some elementary row operations on it, and you get a matrix A2, then we call A1 and A2 to be row equivalent. And can you guess, before I even say anything, what A1 and A2 are going to have common? Since I introduced the rank before, and we said the rank is the maximum, is the number of independent rows. So if I do these row equivalent operations, do you think the rank changes? So the answer is no. So these matrices, we have actually the same rank. Okay? And you see here some of these row operations that basically row operations are nothing else but taking linear combination of the rows of the matrix. But in addition, you can permute the rows, so you can change the order of the rows, multiply rows with scalars, take linear combinations. So this is what we call row equivalent. By the way, I gave you a homework problem that says if A1 is row equivalent to A2 and A2 is row equivalent to A3, prove that A1 is row equivalent to A3. Now, you're going to do that homework after my lecture on Wednesday, where I will introduce in matrix form this type of operations. So you will not know yet on how to do it until the lecture on Wednesday. Okay, so the rank of row equivalent matrices remains the same. So that's nice, which means if a matrix is difficult for us to compute the rank, maybe you know what we can do? We can start doing row operations and maybe come up with a matrix that's very easy to say, the rank is equal to 2, and then we will know what the rank of the original matrix is going to be. That's where we're going to use this. Okay. So let me, again, I'm going to use now only your undergraduate knowledge in linear algebra, or maybe first year freshman, calculus or linear algebra course, so we can communicate this concept of row operations. But again, we're going to do this on Wednesday in a very sophisticated manner using elimination matrices. But let's say I give you this 3×4 matrix that you see here. And I am asking you to find out what's the rank of that matrix. Now, if you look at it for quite some time, you can actually extrapolate what the rank is going to be. But let's say we cannot look carefully on this, okay? So what we're going to do is we're going to try to apply row operations to simplify this matrix, coming with a matrix that is actually easy to compute what the rank is, and then that way figure out what the rank of this matrix A is. So what I'm going to do is I am going to try to eliminate this -6 and 21 below this diagonal 3 on the first row. So I'm going to try to add, if you like, row 2 with some multiple of row 1, and I'm going to try to add row 3 with some multiple of row 1 so I can get rid of -6 and 21. That's what we will call on Wednesday the elimination process, okay? But now we do it with very elementary manners, just for this particular example only. So can you tell me so I need to multiply row 1 with something and subtract the result from row 2. So can you tell me with what should I multiply row 3? So if I subtract it from row 2, I can get rid of -6. Again, what can we multiply row 1? So when I subtract it from row 2, this -6 can disappear. What do I need to multiply so I can subtract? We multiply, and then we subtract. So tell me, what do I multiply, just so we can be precise? -2. So basically, what is -2 is -6 divided by 3, right? That's -2. So if I multiply this with -2, I get -6 here. So when I subtract it from row 2, I'm going to get 0 there. And I refer to -6/3 because we're going to call this a multiplier on the lecture on Wednesday, so it's good to do it precisely. But, again, if you want to simply say, I'm going to take 2 times row 1 and add it to row 2, that's fine. I just told you, no, you have minus the -2 times row 1. Okay, just to be formal. All right, and similarly, I am going to take the ratio of 21 from 3 is 7, and I'm going to subtract 7 times row 1 from row 3, and this is what I get. Nice. Now, this doesn't help me yet, so I'm going to have to do one more elimination. So, and I remind you, this matrix here has exactly the same rank as matrix A. Nothing has changed because we only did linear combination of rows. All right, so can you imagine now what numbers should I get rid to keep going so I can figure out some simpler metrics where the rank is there in an obvious manner? So what numbers should I get rid now? So we're gonna, okay, so we operated here, we put zeros, right? So this is in the diagonal, I'm gonna leave it like that. So we're gonna try to get rid of minus 21. All right, so we're gonna get rid of minus 21. And the way you do this, if you take 1/2 of this row, all right, and you add it basically to this row, then 21 will disappear. Okay? So this is what you get. And again, we're going to do this in a very automated fashion using matrices. So it may look a little bit more complicated on Wednesday. But we get basically this matrix that has exactly the same rank as the original matrix. Can you tell me what is the rank of this matrix? And I remind you, what's the definition of the rank? The number of independent rows. So how many independent rows I have here? Independent. So we have 2. Why is that 2? Because you can get the 0 row by multiplying this by 0 and add a 0, right? The 0, you can derive it by taking linear combination of the other 2 rows. So the rank of this matrix is 2, and the rank of the original matrix is also 2. Okay? So this is what we call elementary row operations. And again, everything that we will do in the next 2 lectures will actually try to make this more sophisticated than what we discussed today, but you can see this as a preliminary fashion. So basically, we're going to dress up this operation with a little bit of matrix operations, so we can generalize it and extrapolate it on how it may work on matrices million by a million, not just 3 by 3. All right. Okay. So you can extrapolate, right, that if I somehow give you a number, let's say, of row vectors, and I ask you how many of those are linearly independent, in principle, what we did will imply take the row vectors that I give you, put them in a matrix form, and compute the rank of the matrix. We agree? I mean, it's the same thing, right? Because by definition, the rank of the matrix counts how many independent rows I have, okay? So this theorem basically doesn't say anything beyond what I just said with words. So it's just a common sense type of theorem. Now, here is something that I would not prove, and it is not as trivial as you may think. It is not as trivial as you may think. And it says, the rank of a matrix also is equal to the maximum number of linearly independent columns. Think about it. We defined the rank to be the number of independent rows, and now I'm claiming that actually somehow it is equal also to the number of independent columns. Now, this would be a nice homework, but not necessarily an easy homework problem. So it's a very sort of serious statement, right? Because why the rows, the way we started, depend on the columns, but this theorem says if you count the number of independent columns, it just happens that is always equal to the number of independent rows, and it's equal to the rank of the matrix, all right? And usually we call the rank of a matrix with little r, okay? So it's equal to r. Okay. Oh, and so I don't miss it, because we defined the rank initially with the number of independent rows, and we said it's the same thing as the number of independent columns. This also implies that A and A transpose have the same rank. All right, so A and A transpose have the same rank. Okay? I mean, in one case, you take the rows of A. If you take A transpose, they become columns. So obviously, it makes sense that A and A transpose will have the same rank. Now, you can put in order lots of sort of very trivial type common sense theorems. So let's look in one of them. Suppose that I give you, let's put this some specific number. Suppose that I work in 3 dimensions, and I give you 4 vectors, all right? Can you tell me if these 4 vectors are linear independent or dependent. So I work in 3 dimensions, and I'm following here what it says. So I give you 4 vectors, p equal to 4, n equal to 3. So in 3 dimensions, if you have 4 vectors, can they be independent? The answer is no, right? Because in 3 dimensions, I only have 3 independent vectors, okay? So if I give you 4, they must be dependent on each other, okay? And actually, you can try, form a matrix, let's say, take a matrix with 4 rows, each of them, let's say, dimension with 3 elements, and try to calculate the rank, and you will see that one of the rows has to be a linear combination of the other rows. There is no other way. All right, so in 3 dimensions, the number of independent vectors you can have is only 3. Okay, it's only 3. Okay, so now we need to sort of generalize things a little bit, and we're going to do this in the context of linear algebra, but the same identical definitions will be applied when we discuss about functions of space and time, when we solve differential equations. So I'm actually, when we reach that point, I will not repeat these concepts because it will be exactly the same as what we do with linear algebra. So if you can use your imagination, and when you see a vector x, if you make that vector x as a function of time, there is a function. But right now, we're talking about just simple vectors. So let's talk about vector spaces and subspaces. So a vector space is a collection of vectors that is closed under linear combinations. Can someone help me tell me what the word closed means? It's a technical term. So when you say it's a collection of vectors, so it's some vectors, and actually can be an infinite, obviously, number of vectors, such that this collection of vectors is closed under linear combinations. What do you think the word closed means? So exactly. So if you take a linear combinations of any of these vectors, the result should also be in that space. That's what the word closed means. And it's a technical term, so I want you to remember it because you will come across in textbooks all the time. So it's a vector space, a collection of vectors, so that if you combine a number of these vectors together, you get another vector in that space. Okay? And this is all actually I want you to know about vector spaces, because I'm going to show you the rest that looks very trivial, and you'll say, do I have to remember all of these things? No, because they're common sense type of properties. The main thing I want you to remember, a vector space has to be such that if you combine elements of that space, you get another element in that space. Okay? That's it. And I want you to remember something else that will come maybe next week in another lecture, which is the following. Let's say that I take some vectors from this space and I combine them, but I combine them with zeros. So 0 times this vector, and 0 times this vector, and 0 times this vector. What do I get as a result? I get the 0 vector. So can you tell me something about the 0 vector and a vector space? This is extremely important. We said that when you combine vectors, they need to be in that space. So I combine them with the zeros, and I get the 0 vector. So what can we say about the 0 vector? Must be in that space. If it is not, then you don't have a vector space. This sounds trivial, but is essential. Very essential for many, many things we're going to be doing, right? So the 0 vector is there. Okay? All right. So I'm going to give you now the rest of the properties of a vector space. You look at them, they sound trivial. The only thing I want you to remember without having to look in any books is vector space, if you combine elements, you get another element in that space. That's all. Done, okay? But let me show you some other formalities so we can be a little bit precise. I'm going to come back to this, so I'm going to bypass it. So here are the formalities. So we said the combination of the vectors has to be in that vector space as well. But in addition, some very common sense properties need to be satisfied. And I'm listing here under 2 this type of properties. So if A and B are in that space, then A plus B equal B plus A, which means you need to define an operation that we call the sum operation. Right? You need to define what that plus means, all right? And that plus has to be such that A plus B equal B plus A. Now, it may sound trivial. I know how to add vectors. But, this concept is way beyond vectors. You can take these elements of this space V to be, what can they be? Matrices. Can they be tensors? Can they be functions? So if you defined an operation that you like, and you say, I'm going to call this the sum, then the following properties need to be satisfied. A plus B equal B plus A plus B, parenthesis plus C. You can change the order of parentheses, and this is A plus B plus C. You need to define a 0 element, right? And you need to define a negative element, so when you add A and negative A, you get 0. Again, nothing fancy. And then you need to be able to define multiplication with a scalar. And again, these are common sense things, okay? So C parenthesis A plus B, CA plus CB. If you have 2 scalars together, you can distribute this as CA plus KA. You can change actually the parentheses when it comes to the multiplication by scalar, the way you see on property C on the right. And of course, if you multiply with number 1, nothing changes, you get back A. Again, really what I want you to remember is that this linear combination properties and that the 0 belongs in that space, okay? The rest are properties that you can always look in the book. They look like this, okay? And most of them are common sense because all of you know what addition means and multiplication with a scalar means. But if you use your imagination, you can make this addition to be something very weird, something different, okay? Not your common addition. Well, in that case, you need to be sure that you satisfy these properties. And if you do, then you can apply the same machinery as we learned today. All right. So I am not going to basically repeat the same thing, so in a more formal way, so you guys can read all of this, okay? And so I'm going to just bypass them and go to slide here 84 to define the basis of a vector space. So we already discussed about linear independent vectors. And we said the vector space is a collection, an infinite collection, let's say, of vectors in our case. Can you tell me, what would be the dimension of a vector space? What would be a nice definition? A nice common sense definition. So a vector space consists of many, let's say, we work with vectors, right? All the 3-dimensional vectors. So what will be a nice definition based on what we know for the dimension of the vector space? What will be a nice definition? I mean, in 3 dimensions, right? I can have millions of 3-dimensional vectors. But what is the dimension of the vector space? What should I define as the dimension? And most probably it says there, right? It says the maximum number of linearly independent vectors on the vector space. So if we are in R cube, right, the maximum number of independent vectors, it's 3, okay? So obviously in this case, to make things easy, we assume that the dimension of the vector space is not infinite, okay? And if you take the maximum number of linear independent vectors in that space V, then we call that the basis of the vector space. And I think we talked about this in the lecture last week, right? So if you take the maximum number of independent vectors in V, and the idea here is that this maximum number of independent vectors in V is what you need to generate any other vector in V by what process? Linear combinations, right? So the basis of V is basically the maximum number, right? Consists of the maximum number of independent vectors. And what I mean a maximum number, that if you try to add one more vector to the basis, that vector will be a combination of the previous vectors. Okay? And this is what we call the basis for the vector space V. And we said something last week. Is this basis unique? So in 3 dimensions, do I have a unique basis? Nope. Okay? So we don't say the basis, we say a basis, okay? There's maybe multiple bases here. And actually, one of the tricks of linear algebra, if we do the course correctly, you will see that in many of the calculations later on, it will be all about what is the best basis to do calculations. Okay, what is the best basis to do calculations? So that the algebra is very simple. Okay, and we will see this as we move along. All right, another concept now, extremely fundamental since we talk about basis and the dimension of a space. So let's suppose that I give you a bunch of vectors. Let's say 10 vectors in 3 dimensions. I'm saying here's vector 1, 2, to vector P in this case. So what I'm going to do is I'm going to create a space by taking linear combination of these P vectors that I gave you. I repeat, I give you only 10 vectors, P equal to 10 here, and then I create a space that consists of vectors that they are linear combinations of the vectors A1 to AP. That's my vector space V. So the word that you use is that these vectors span the space that I just produced. So I said I take combinations and I come up with some vector space. So this vectors A1 to AP basically span that vector space. Or in other simple words, that vector space is the span of the vectors A1 to AP. Any way you want to see it. So I give you a bunch of vectors, right? You take, I don't tell you if they're dependent, independent, it doesn't matter. You combine them. That space that you create is the span of these P vectors. Okay? We haven't said if they're dependent, independent, it doesn't matter. You combine them in any possible way, that is the span, which is a vector space generated by A1 to AP. Okay. Now, if it happens that these vectors are linearly independent, what can you tell me about the basis of the span of these vectors? So remember, I create a vector space by taking combinations of these P vectors. And now I tell you that these P vectors are independent. Right? So what is the dimension of this space that I created? The space that I created only consists of linear combinations of these P vectors, nothing else. Right? This is how I define it. So if I take, P independent vectors, what's the dimension of the space that you're generating by taking combinations of these vectors? It's P. So in that case, these vectors form a basis of the vector space that we're referring to, okay? And so the idea here is for when you generate a space by combining vectors together, these vectors have to be linear independent, and because we're referring to the vector space V being the span of the A1 to AP, every vector in V has to be a linear combination of these vectors A1 to AP. So let me, this is going to be something that I want you to, when you talk about linear algebra, to always sort of use this terminology, right? If you take vectors, a few vectors, you combine them, the vector space you produce is called the span of these vectors. Okay? It doesn't matter if they are dependent, if they're independent, or, Now, if it happens that they are independent, then they form a basis of that span that they generated. Okay. Obviously, we are going to do a lot of algebra on the space Rn. So these are vectors with n components with elements that they are real numbers. This is how we denote this. And the dimension of this vector space, of course, is equal to n. All right. Now, another not a very easy concept, and we will elaborate on this, for sure. Next week, we will devote a whole week actually on vector spaces. But let me just define what is a subspace of a vector space V. Don't read anything. Just start using common sense and tell me what potentially a subspace of a vector space is. So I have a vector space, let's say in 3 dimensions or in 10 dimensions. What potentially should we define as a subspace of that vector space? Think in 3 dimensions, right? Can you tell me what you will call a subspace in 3 dimensions? So here's 3 dimensions. What will be something that you say with common sense, that's a subspace? Any plane?
One passed through the origin.
Why pass through the origin?
Because there would have to be a space itself.
Exactly. So the subspace is part of the bigger space that you work on, right? But that bigger space has to satisfy the same properties as the original space, which means if you take linear combinations of vectors in that subspace, they have to be on the subspace, which means 0 has to be in that subspace. Which means if you have in 3D and you take this plane that doesn't pass from the origin, it's not a subspace. And we will see this actually with plots and everything in a forthcoming lecture. The idea here is the subspace, right? It is a subset, if you like, of the vector space, okay? But it needs to satisfy the same properties that the vector space V satisfies. And primarily, you need to remember if you take linear combinations of vectors from that subspace, they need to be in that subspace, which means 0 has to be there. If 0 is not there, this is not going to be a subspace. So can someone give me all the subspaces of the 3-dimensional space? There's a few of them. So all possible in 3 dimensions, what are all the subspaces that you can have? So a plane through the origin 1. Okay, continue. The 0 vector itself does it. Excellent. Give me another one. A line through the origin. Okay, did we miss anything else? We must. The whole space itself. Right? We said the origin. So if you take the whole space itself, it's also a subspace of itself. Okay? All right. Now, you may say, but lots of things I learned in my courses, I always work with planes that don't pass from the origin. Yeah, but we are doing things seriously here. In linear algebra, if you try to do operations with vectors on planes that don't pass from the origin, you may get in trouble. And we will see how on the lectures next week. Okay? All right. So, and again, the only thing I want you to remember is, so a subspace is to satisfy these fundamental properties that if you take linear combinations of vectors on that subspace, they have to be on that subspace. Okay? All right. And these are the 4 examples you told me for the subspaces in our cube. A line through the origin, a plane through the origin, the whole space, and of course, the 0 vector. Okay, now we're gonna really move ahead of our schedule, and I'm gonna start throwing to you some fundamental spaces for matrices that are derived from matrices, okay? If you don't understand everything yet, okay, there will be lots of lectures coming up on the topic, but also there is a homework you have to work on, so you have to understand something, okay? All right, so I'm going to define the column space of A. So I give you a matrix A, and I want to define a space that I'm going to call the column space of A. And remember, if I give you vectors, right, you can combine them, linear combination, and you get what we call the span of those vectors. So what do you think the column space of a matrix is? The common sense definition. So I have a matrix A, m by n. So what do you think the column space of A would be as a nice definition? Will be the space that is generated by what? By linear combinations of the columns of that matrix. And we call that the column space. Okay? You know, obviously, you thought in lecture one, you know, this guy is going to bombard us with matrices one by one and the inverse, etc. But, you know, we will do lots of things about spaces with matrices because there's no way we can actually use those ideas to do differential equations unless we understand something fundamental about spaces. Remember, there will be lots of concepts. The algebra will actually be trivial in most cases. I will never ask you to do anything on 50 by 50. Maybe we will go to 3 by 3, 4 by 4, but that's it. Simple things, okay? So I want you to learn the concepts. So the column space of A is the space that is produced by taking combinations of the columns. So if I have a matrix A in R m times n, I denote the column space as C of A. Okay, that's C of A. Question. The matrix is m by n. Can you tell me, so the column space I can tell you is a subspace of another bigger space. Can you tell me of what space the column space of A is a subspace of? Remember, the matrix is m by n. So the column space is a subspace of what space? So every vector in the column space has how many elements? If the matrix is m by n? How many? M. So the column space is a subspace of what space? Say it again, I heard you. R, no, we said the column space has m elements, right? So the vectors in that space have m elements. So the column space C of A is a subspace of R to what power? There are m-dimensional vectors, so it's a subspace of Rm. Okay? I mean, they're column vectors. They, you know, they have m elements. Okay. So, so the column space is a subspace of Rm. All right, this is very nice. And let me just tell you why these techniques are so powerful, right? Even though we will do this later in the course, let's say we want to solve Ax equal B. So I give you A and I give you B. You remember that when you take the product Ax, what do you produce? You produce a linear combination of what? We did this in another lecture. When you take A times a vector x, you produce linear combinations of the columns. So Ax belongs to what space? Ax belongs to what space? The column space of A. So the only way for Ax equal B to have a solution would be for B to belong where? To the column space. Done. If B is not in the column space of A, this system has basically no solution. Okay? And again, we will see this later on again. So let me define another space. And this will be the null space of A, and will consist of all vectors x, so that Ax equal to 0 vector. And so you can think of this, we discuss AX equal B. This is the homogeneous equation, right? Where the right side is 0. So the null space is all x's so that AX equal to 0. And you can show actually that this is a vector space. I mean, you can take x1 and x2 that satisfy this equation, take a combination, you will see the combinations also will be in the null space. Okay? Can you tell me that the null space will be a vector space, will be a subspace of what space? Again, A is m by n. So the null space will be a space, a subspace of R to the power n. Right? You can see A times x, so x has dimension n, so the null space is a subspace of Rn. Okay? So remember the column space, columns, M, subspace of Rm. The null space, it's a subspace of Rn. Okay? And the notation we use for the null space is n of A. Okay? So the column space, linear combination of the columns, and the null space defined by the solutions of AX equal to 0. Okay? Now, obviously, the implication here, right, when you define the null space is that in many matrices A, the solution to x equal to 0 will not be x equal to 0 alone. There will be other x's that they are not 0 that satisfy this equation. And we will see lots of examples on this topic. All right. Can you tell me what the row space will be? Actually, to define the row space, you don't even need to, introduce another extra definition, right? Can you take the rows of a matrix and make them to look like columns? What matrix will you produce if you take the rows and you make them columns? The transpose of the matrix. So what would be the right definition for the row space of A? To be the same as the column space of which matrix? Of A transpose. Okay? So can you tell me the row space of A that we denote as the same thing as column of A transpose, this is how we write it. Can you tell me it's a subspace of what space? Rn. Well, I mean, you look at the rows, right? And you say what space they, how many elements? I have n, so Rn, exactly. Okay? And you remember something that I said that I did not really prove. I said that the number of independent rows is the same as the number of independent columns. So what can you tell me about the dimensionality of the column space and the dimensionality of the row space? If that statement was correct. Has to be the same. All right? And we know actually what notation we will use. This have to be the same and equal to the rank of the matrix, which we call it R. All right. So I'm going to give you something to use your imagination. This is like 4 lectures ahead. But I want you to just to use your imagination. Why is that possible? Okay? Don't read anything that is written there. I want you to look only at this equation here. R plus n minus y equal to n. Okay? So remember, R is the dimensionality of the row space. Right? That's the rank. That's what you told me. The number of independent rows. Okay? So this equation says that the number of independent rows, the dimensionality basically of the row space, plus this is actually, okay, I'm giving you the answer, no proofs. This is the dimensionality of the null space. So when you add the two things together, this is equal to n. So can you use your imagination and tell me what exactly that means? Because it's very weird. It says, so the row space and the null space, they're all subspaces of what space? R to what power? N. And here what I tell you is the dimensionality of the row space and of the null space, together, they give you the whole dimensionality of Rn. So if the row space is this plane, what does this equation say? Where is the null space? Because it says the row space plus the null space basically give you the dimensionality of the whole Rn space. So if this is the row space, where is the null space? Geometrically. It's basically orthogonal, even though I have not defined what orthogonality means. But you can appreciate if one space is all the vectors on this plane, right? Then the null space has to be orthogonal, so the two things together give you everything in 3 dimensions, let's say. I left that space out. There is a 4th space that is what you're referring to, and is going to come in 1 week from today. Okay? So that will complement the column space, if that's what you had in mind. Okay? So the idea here is, right, that we actually, to generate the whole space in n dimensions, we really have to find this dimensionality, if you like, the rank of the row space, and then find the solutions to the null space, and the two together give you everything in the n-dimensional space. This is wonderful, right? I mean, you have basically decomposed the solutions of of any vector in n dimensions to vectors basically that are produced by linear combinations of the rows plus the solutions coming from the null space. And you have a homework, actually, where you have to do this on homework 1. OK, it's 11:17, so I have 3 minutes left, and hopefully we can finish this. So we define vector spaces, right? We said linear combinations in a vector space are back in the vector space. So let me expand a little bit, and I'm going to define what is called an inner product vector space. Basically, what is the idea of this inner product vector space is basically it's a vector space that, in addition to everything we discussed today, I also define an inner product between its elements, like a dot product for vectors. And this inner product has to satisfy 2 nice properties that you already know, and they're common sense. The second property is the symmetry. So the inner product of A and B has to be the same as B and A. And then the linearity, where Q1 and Q2 are scalars. So if you have a vector space and you equip that vector space with an inner product, okay, then we call this an inner product vector space. And most of the spaces we will work in this course have an inner product assigned with them. Certainly if you play with vectors, right, we already have defined what this inner product is. Now, you can generalize these concepts to very complicated situations, so don't consider this as trivial things, right? Because I can tell you there are lots of inner product spaces where this symmetry condition is not satisfied. Yeah? Which vectors are scalars? Yes, it's a scalar, yes. So the inner product space, right, is a space where, in addition to the properties we have seen, you also define what this scalar affiliated with the vectors A and B is about. And you remember we defined it for vectors earlier on, and we said it's the summation of the products of the components of A and B. So that's a definition that satisfies actually these 2 properties. So the resulting space, we call it an inner product space, or Hilbert space, which we leave it for another day. Okay? All right. So let me just give you some fundamental things. Obviously, earlier on in the course, we defined A dot A to be the magnitude of the vector square. but actually, to be more general in the notation, the inner product of a vector with itself, we're going to call it the norm of the vector square. The norm means, you know, the length, all right, the length square. And it satisfies these two properties. If the length is 0 or the norm is 0, can only happen if the vector is a 0 vector, right? You cannot have the vector or the magnitude of a vector to be 0 unless the vector is equal to 0. Okay. Now, the rest of the things you already have seen them, so I'm only going to put them there because it's 11:20. So let me just list some fundamental properties that you can prove for any inner product vector space. You remember the Cauchy-Scwartz inequality? From where did I derive in another lecture for vectors? Where did this thing come from? You remember we managed to write the inner product as the magnitude of A, the magnitude of B times the cosine of an angle between A and B. And because the cosine of the angle is in absolute value less than 1, there is the Cauchy-Scwartz inequality. Very important, actually, inequality that would be very handy in calculations. Now, using the Cauchy-Scwartz inequality, you can actually define the triangular inequality. You can prove it. And the way to prove it, as I told you, is take the square of this and expand the magnitude square as the inner product of a vector with itself. And then you use this Cauchy-Scwartz inequality to prove the triangular inequality. And then finally, you can prove this parallelogram equality that you see on the bottom. Okay? And again, if you expand it, everything will cancel out except you're going to have 2 times the inner product of A and B minus 2 times the inner product of A and B. All right, so I'm going to finish there. And so let me kill the video for the day. And so I will see you on Wednesday.